Today, everybody. So today in this video lesson, we're going to learn about atomic models. We have already learned about the discoveries of these fundamental particles, that is, the subatomic particles that are present in an atom, namely the protons, the neutrons, and then the electrons in the last video lesson. So now, having learned about the discoveries of these subatomic particles, namely protons, neutrons, and electrons, the next thing is regarding the structure of an atom. Now, we are faced with the problem regarding the structure of an atom. Let's see how these protons, neutrons, and electrons are actually present in an atom as such. So now different scientists, they did various experiments and then came up with their own models of the structure of an atom to begin with. So now you'll see that we first going to take up what is known as the Thomson model of atom. It was sometime towards the end of the 19th century. So this J.J. Thomson, he came up with this model of an atom. So Thomson's model of atom, here J.J. Thomson has said that an atom possesses or has a spherical shape in which the positively charged protons are uniformly distributed and the negatively charged electrons, they are embedded into the positive charge, so as to give a sort of very stable kind of electrostatic arrangement to the atom. This was the structure proposed by Thomson. So you see that J.J. Thomson said that an atom possesses, or it has a spherical shape in which the positively charged protons are distributed uniformly, and then the negatively charged electrons are embedded into the positive charge in such a manner, I should say, so as to give the most stable electrostatic arrangement to the atom. That is why the Thomson model of the atom is also called the plum pudding model, or it is also called the raisin pudding. It's pudding, sort of cake-like thing in which you have like plums sprinkled over it, or like raisins being sprinkled over your pudding. And it is also called a watermelon. That's because, like, when you cut a watermelon into two halves, you will see the red fleshy part and then the seeds scattered across. So like the red fleshy part can be thought of as your positively charged protons, and then the negatively charged electrons are similar to, the seeds here, they can be treated as your electrons. So these different names are given to Thomson's model of atom. And now, the next thing is, now we are going on to the next part, that is Rutherford's nuclear model of an atom. But before that, let me tell you a few words on radioactivity. Radioactivity. Now, radioactivity, it was actually discovered by Henry Becquerel again sometime back here towards the end of the 19th century or beginning of the 20th century. Now, talking about radioactivity, some elements have the property of emitting radiations on their own. So, this phenomenon of some elements having the property to emit radiations on their own is called radioactivity, and these elements are called radioactive elements. So there are many radioactive elements, like for instance you have actinium, there is thorium, there is polonium, uranium, protactinium, and so on. So there are many of these radioactive elements. So these elements, they can emit radiations on their own. So during sort of radioactivity, what happens is these radioactive elements, they emit these different sort of radiations or different rays. So there are mainly three types of rays that are emitted during radioactivity by these radioactive elements, and these are you have what are known as the alpha particles. Then there is the next one you have is the beta particles, and then the third one you have, these are called the gamma rays. Now, as far as alpha particles are concerned, these are high energy particles having 2 units of positive charge and 4 units of atomic mass. So these alpha particles are actually nothing but they are your helium nuclei, that is the nucleus of helium. When an atom of helium loses its 2 electrons, then it becomes a helium ion, that is He2 plus with 2 positive charges, and then there are 4 that is nucleons, protons plus neutrons inside the nucleus. So these are positively charged particles. And then next you have the beta particles. The beta particles are negatively charged particles, and they are similar to your electrons, right? And then the third thing is your gamma rays. Now these gamma rays are like your X-rays, and they have no charge as such. They are neutral in nature. Now it is said that these alpha particles they have the lowest penetration power as such, and then next you have the beta particles. They are said to be having more penetration power than alpha particles. They are said to be 100 times more powerful as far as the penetration power is concerned. It is 100 times more penetrating than the alpha particles, and then the penetration power of the gamma rays are said to be 1,000 times more than that of the alpha particles. So this is what I can tell you about these radiations that are emitted during radioactivity. So now next we shall move on to Rutherford's nuclear model of atom. So based on this, we talk about something called this is I'll just write about this, Rutherford's nuclear model of atom. So now, as far as the Rutherford's nuclear model of atom is concerned, you will see that Rutherford, he did this experiment by making use of a very thin foil of gold, or a very thin sheet of gold, which is said about 100 nanometers in thickness. 100 nanometers, very thin it is actually. And then he's said to pass these alpha particles through this thin sheet of foil of gold, And in his experiment, now let us see what all things happen actually. So he passed a stream of alpha particles through very thin foil or sheet of gold, and the observations. See, like now this is supposed to be just one atom of gold in that thin foil of gold. So you will see that these are your alpha particles. They are now seen passing through the atom of gold, and you see that most of these alpha particles, they are seen passing straight through the gold foil or through the atom of gold without any deflection as such. So they are passing straight through the gold foil or through the atom. And then you can see that few of these alpha particles getting deflected through some angles. That's the second thing. And then the third thing is you can see one alpha particle here. That is, very few alpha particles were seen getting bounced back, by almost 180 degrees. This is what was observed actually in Rutherford's alpha particle scattering experiment. And in fact, to have a better understanding of this experiment, he instead of used a sort of circular fluorescent screen, and this can be understood better if you have a look at this picture here. See, now here you have the source of your alpha particles coming from here, and then they are going to pass through the thin gold foil here, and then now this is the circular fluorescent screen, and once these alpha particles pass through the gold foil there, this fluorescent screen here, it is in fact coated with a fluorescent material like zinc sulfide. So once these alpha particles, when they strike the fluorescent screen, one could observe these flashes of light or these spots, bright spots. So this is what happens. Like here we see that these flashes of light or these bright spots were seen at different places on the circular fluorescent screen, indicating that these alpha particles, they just don't go in one direction, so that they are getting scattered as such. So here, on the basis of this experiment, you will just see, we will discuss this, that is experimental observations of Rutherford's alpha particle scattering experiment. Now these are as follows. The first one, as you saw in the picture here, like most of the alpha particles, they pass through the gold foil undeflected. In the sense, like most of these alpha particles, they did not get deflected when they pass through the gold foil, right? This was the first observation. Then a small fraction of the alpha particles, was seen getting deflected through small angles. That is a small fraction. That means a few alpha particles. They got deflected through small angles. They did not go straight as such. And then the third observation was very few alpha particles, very few, and approximately 1 in 20,000 of these alpha particles. So they got bounced back. That is, they were deflected by almost 180 degrees. Now, based on these observations, you will see that this Rutherford, he came up with these important postulates or conclusions, I should say. And today we talk about what is known as Rutherford's nuclear model of atom. So the important postulates of Rutherford's nuclear model of atom are the first one. The first important postulate is, see, most of the space in an atom is empty. So you should know that most of the space in an atom is actually empty, that is because most of the other particles pass through the gold foil undeflected. Since most of the other particles pass straight through the gold foil, they didn't get deflected as such. So the conclusion here is that most of the space in an atom is empty. That's one thing. The second postulate is we saw that a few of these other particles got deflected through some angles, right? So the deflection of a few other particles must be due to an enormous repulsive force, showing that most of the positive charge and the mass of an atom is not spread throughout the atom, as was believed at that time, but concentrated in a small region of the atom, which he called the nucleus. So now here, the deflection of a few other particles, like we saw that a few other particles they got deflected through some angles, and then a very few other particles, like I said, 1 in 20,000 other particles got bounced back. So these deflections, or bouncing back of a very few of these other particles, show that most of the positive charge and the mass of an atom is not spread throughout the atom. It is not spread throughout the atom, but they are concentrated in a small region of the atom, which he called the nucleus. That's the second point there. And then the third point is the electrons surround the nucleus and move at high speed around the nucleus in circular paths called orbits. So here, regarding the electrons, Rutherford said that these electrons, they surround the nucleus and then they move at high speeds around the nucleus in circular paths called orbits, right? Then the fourth point here is the electrons and the nucleons are held together by electrostatic forces. So these electrons and then the nucleus of the atom, they are held together by electrostatic forces. The electrons do not collapse into the nucleus because the revolving electrons produce centrifugal force, which balances the force of attraction between the nucleus and the electrons. This is what is said. So like these electrons, they move around the nucleus in fixed circular paths called orbits, and then they don't sort of collapse or fall into the nucleus. And that's because it is said that even though there is this force of attraction between the nucleus and the electrons, but this force is balanced by the revolving electrons, which produce what is known as the centrifugal force. So this thing called centrifugal force, it balances the force of attraction between the nucleus and the electrons, and that's why the electrons, they remain outside the atom in the orbits, outside the nucleus, right? In the orbits. And then the final thing is, now calculations by Rutherford showed that the volume occupied by the nucleus, approximately, that is 10 raised to power -15 meters, that is the radius, is negligibly small as compared to the total volume of the atom, which is 10 raised to the power -10 meters. I'm not tapped it here. Anyway, so the volume occupied by the nucleus is very small in size compared to the overall size of the atom here. That's because the radius of the nucleus, that is the size of the nucleus, is 10 raised to the power -15 meters compared to the size of the atom as a whole, which is 10 raised to the power -10 meters. So which is that is much bigger. Okay, so now this is all about the important postulates of Rutherford's nuclear model of atom. And now before that, we're going to work out some problems based on protons, neutrons, and then electrons, right? So here, let's move on to the next part.